Okay, we're going to kind of continue with what we were doing on Friday in terms of magnetic fields. Everybody remember all the right-hand rules?
Yes.
I forget.
Okay, just a reminder. First one is a magnetic field around a wire, and that you point your thumb in the direction of the current and your fingers curl in the direction the magnetic field goes, so it goes around in a circle. Okay. It is on the other, like Friday's class is online, so. Okay, the other one, you take your right hand, make it flat, your fingers point in the direction of the magnetic field, thumb is the current, and palm is the force. Does it sound familiar to those of you who are here?
Yes.
Okay. Alright, so we're going to talk about today, it's going to be a decent review for those of you who are here, and hopefully those of you who weren't here will be able to catch up a little bit, is the force on current carrying wires that are near each other. So if you have two current carrying wires, they exert a force on each other because each of them has a magnetic field. Okay. So first thing, we want to figure out the force this bottom wire exerts on the top wire. So first thing we want to do is figure out the magnetic field that the bottom wire generates. So on top of the bottom wire, which direction is the magnetic field going?
Down. Back.
Back.
Out the page.
Out of the page. Does that make sense, everybody? So we pointed for the bottom wire, pointed our fingers, or pointed our thumb in the direction of the current, so this way, right hand. And then on top of it, your fingers are curling out. Does that make sense, everybody?
Yes.
So, and to make something point out, we represent it with little dots.
How come you know it goes this way, not like this?
Because what you want is what are your fingers doing when they're on top of the wire? Going out. When they're out this side point, now they're going down. What are your fingers doing when it's on the bottom of the wire? Going into the page. So this would be X's for into the page on the bottom of this wire.
Why'd you put those X's there?
Above this wire it's going into the page, below the wire it's coming out, or above the wire it's going out of the page, below the wire it's going into the page.
Why do you make two rows?
Just because. There's no real reason for
I don't know
that.
if there's like a specific reason.
Okay. You said it's going out and then going in.
Yep, out on top, in on bottom. Alright. Okay. So what we're worried about is the force in this top wire. So we want to figure out the magnetic field around that. So at that point the magnetic field is going out. Does that make sense to everybody? So now we use the other right hand rule. We point our thumb in the direction of the current. So our thumb goes this way. I'll be like you guys. Thumb goes this way. Is a magnetic field around the top wire going out or in? Out. Out, so we point our fingers in the direction the magnetic field is going. And what direction is the force?
Down.
Down. So the force is pointing down on that wire. Okay. And now, sort of because of Newton's third law, but we could also do this the other way. Since the force in this one is down, it has to be an equal and opposite force in this one, so it's going to be force up. And when the two wires' currents are going in the same direction, they attract each other. So the forces bring them together. Does that kind of make sense?
Did you do a little thing for the bottom one?
Do you want me to do a little thing for the bottom one too?
Yeah.
Okay. Let's do a little thing for the bottom one.
Or do we just know that the bottom is opposite?
You can know that the bottom is opposite, but it might be good for me to do it anyway.
Okay.
Okay, so now we're doing the top one on the bottom. So what we're really worried about is the magnetic field below this one. So is that into or out of the page?
Into.
Into. I'm just going to draw some X's. So around that wire, the magnetic field's going into the page.
Why are you concerned about the bottom of the wire?
Because we're looking for the magnetic field generated by this one, and the other wire is below it. So we're looking for like the magnetic field below that top wire. Does that make sense, Laura?
But why are the two wires like not the same?
They are going to be the same. Like they're both going to be attracted to each other, but it's good to do them both. Does that make sense?
Yeah.
Okay.
which one's the X's and which one's...
X's go into the page, circles go out of the
Yeah,
page.
but like on which wire doesn't matter.
It does matter. Right. Look, okay. I feel like you guys don't know what you don't know. It's part of the problem here. Okay. So, everybody, do you guys understand how we got the X's and why they're not circles?
Yeah.
It's going into the page.
This going into the page. Because point your thumb in the direction of the current, and your fingers curve into the page below it. What?
Why would they be the same?
How
why
do
are they
you-
the same?
I don't understand what you guys are saying.
I'm
Well, I don't
Why-
curious as to
understand.
where
They're two
we're putting
identical
these
wires.
situations from. Like, why are our fingers pointing this way?
Okay, this is something that I think you guys are having a lot of trouble with right now, is below the wire and above the wire.
Which wire?
The top one.
Which one is it?
We're dealing with the top one, the magnetic field from the top one, and that's going to affect the bottom one.
Okay, bro.
Okay, so does everybody understand that point your thumb this way, on the bottom it's pointing into the page.
Yes,
Okay, and the top would be pointing out of the page.
correct.
Okay, so that's why we have the X's down here. Does that make sense to everybody?
Yeah.
Okay, so the magnetic field is pointing into this page for the bottom wire. Now we take our hand, thumb in the direction of the current, fingers into the page because that's the direction of the magnetic field. Palm is pointing up, so the force is up. So both forces are going in opposite directions, so they're attracting. Does that make sense to everybody?
Yep.
Alright, now we're going to do two wires carrying current opposite direction. Okay, so if we find the force on one, we'll know the force on the other. Okay, so let's figure out the magnetic field from the bottom one on the top one. So we want to find the magnetic field above the bottom wire, into the page. Does everybody understand why that's into the page?
Yes.
Okay. So we have the magnetic field is into the page. Now we figure out the force on the top wire. So point your thumb in the direction of the current of the top wire. Fingers into the page. What direction is the force on it? Up. So what direction is the force on the bottom wire going to be? Down. Okay. So if they're carrying current in opposite directions, they repel each other. If they're carrying current in the same directions, they attract. Does that make sense to everybody? Okay. Okay. Now we're going to go through a couple more concepts here. Solenoids and electromagnets. Alright, now you guys have heard of an electromagnet before. What does it do?
It magnetizes uses electric current. Magnetic field.
Okay, everyone at one time, that way it's really easy to understand it, you guys. Okay, so electromagnetic or a solenoid, they're kind of the same thing. They use a current or electricity to generate a magnetic field. How they do it is they take a loop of wire, wire keeps going around in circles. Number of loops matters, we'll talk about later when we get to the math of these. And the magnetic field of all these loops keeps adding up. So magnetic field is always going like this, and it always points down on the outside and up on the inside in this case. And actually these lines are drawn backwards on this one. This is not a correct picture. I pulled it from the internet, which is probably not a good thing without really checking it. But it's backwards. Anyway, but all the magnetic field lines from each coil of wire keeps adding up. So the more coils of wire you have in a certain amount of space, the more magnetic field is generated. Does that kind of make sense how that works?
Yeah, bro.
Okay. Okay, so some demos here. Here we go. I have way too many things up on my computer. There it is. That. No, go back. No. how these little like compass needle looking things on there?
Right.
True.
That's the magnetic field. So if we move the magnet, generates magnetic field different places, and the compass moves. Yay.
Yay, compass.
Okay. Alright, this is kind of the big concept for the rest of the stuff we're going to talk about. All the magnetic field lines, you see these two loops of wire? If the number and strength of the magnetic field lines or the direction going through this loop of wire changes, electricity or current is generated. So if I move this magnet closer to it, the light bulb lights up. Or if I move it away from it, the light bulb lights up. This is how all generators work and generate electricity. This is this basic idea. So the number of electric field lines going through that loop of wire changes, electricity is generated. If I just leave it there, no electricity is generated. The amount of electric field has to be changing for electricity to be generated. Does that make sense to everybody? So do you guys understand the magnetic field line thing?
What happens if I make more loops?
If you make more loops,
More look.
Same thing?
same thing, but more electricity is actually generated with more loops.
So more light.
More light.
How many loops can you get?
3.
Sorry.
It's not very
That's
exciting,
it?
I'm sorry.
It's okay.
Okay, so this is in general how a generator works.
What?
That's awesome.
This is a faucet.
Oh, that's sweet.
Okay, oops, that's not what I wanted. So you see how all the little things that indicate magnetic field are changing all the time? That means there's current being generated all the time. Does that kind of make sense to everybody? So what happens, you see, when the ones inside the loop of the wire change, the electrons move and electricity is generated. And because this is spinning all the time, they're always changing, so electricity is always being generated. You guys can understand this?
That makes sense.
Is this how like a dam works?
This is how this is a very simple illustration of how like a dam works to generate electricity, like the Hoover Dam.
Don't say that word.
You have water flowing through it, causing generators to spin all the time, and those generators cause the magnetic field inside the loop to change. Really what happens in a generator usually is the magnet staying the same and this is spinning instead, but this is a little easier to illustrate for our purposes. Brian?
Would it, like this model, would it be more effective to have like 2 magnets like this and a cross? Or would it do nothing? Like,
What matters is the strength of the magnetic fields. So the stronger you can make the magnets, the better it's going to be.
So is there a slight like, you know how the light's like kind of smaller and then bigger? Is there like a very slight that we just can't see with our eye?
Okay, there is a time when this goes to 0, like when because it's changing direction all the time, it speeds up, slows down, but it does go to 0. But that 0, it's 120 times per second in our outlets. So it's way too fast for our eyes to
For
pick
us
up,
to pick up.
and it doesn't even affect the lights right.
How come the magnet doesn't have to go through the loops?
I saw it.
How come the magnet doesn't have to go through the loops? All that matters is the magnetic field through the loops, not the magnet through the loops.
Then on the last one, how come there wasn't electricity unless the...
Let me show you here again. Okay, so even if I go over here, do you see how it's still lighting up?
Oh, you're just going too fast.
Yeah. So even if it's
Yeah.
not going through the loops, it still lights up. Do you guys understand the generator thing? Okay. So here's this is an electromagnet. So you have the coils of wire that keep generating a magnetic field. If it's direct current, like from a battery, it just stays the same. So one end's this side's the north pole of a magnet, this side's the south pole of a magnet. Now if we switch it to AC current, which means that it alternates between going one direction and going the other direction for an AC current. Now do you see how the magnetic field lines keep going back and forth and keep changing? Everybody understand that? And that leads us to the last kind of type of electrical device we'll talk about here. That's a transformer. So you see we have this coil of wire is generating a magnetic field. Nothing's happening to this one because the lines through this loop are not changing. But if we switch the first coil of wire to AC current, now do you see how they keep going back and forth and they're constantly changing? So the light bulb keeps lighting up. Does that make sense? And this is called a transformer, and it usually is used to transfer something from low voltage to high voltage or high voltage to low voltage. We'll talk about how it works later on when we get to the math part. Kyle?
So like in our house, if it moved slow like that, would our lights
Yeah, your lights would like
go off and on?
pulsate if the alternating current was going up and down more slowly. Because it does go to 0 with alternating current.
How do I make that happen?
You can't. Unfortunately, it's the power company that determines how the pulsation.
So transformers are basically just used to change from low to high.
Change to low to high voltage. The reason you change from low to high or high to low is it's more efficient to send electricity through power lines at high voltage. So what they'll do is use what's called a step-up transformer at the power station, like where the electricity is being generated, to make the voltage up to like maybe 10,000 volts. The voltage goes 10,000 volts to the power lines, which lowers the amount of electrical power lost. Then it's stepped back down to your house to get back down to 120 volts. Because if your wall outlets were at 10,000 volts, when you'd walk by, like electricity would jump out and shock you and maybe kill you or something like that.
That would be fun.
So why can't you like just use like a tiny energy source, but use just a transformer to
Bump it up.
like bump it up? And
What happens is you increase the voltage, but the current decreases. So if you look at here, you see how these ones are moving more than these ones? So the voltage increases, but the current has decreased. So the power, so the overall energy stays the same. So you can't like generate energy by keep stepping up a transformer. John?
So since these things aren't like connected, couldn't you like use something from the transformer or something, but outside of it, like have something powered by something sitting over there?
Well, this is the idea behind what's called a Tesla coil. So a Tesla coil is like a really, really giant, this is Nikola Tesla's idea, that wireless electricity, a really, really giant one of these. And then like, for example, like your TV would have loops of wire, and just because the magnetic field was constantly changing, it would generate enough electricity for your TV to work. And those actually did work. He made one, like a giant tower of it, and it worked for like 500 feet. The problem was, like you could generate electricity for like 500 feet from this Tesla coil, but you couldn't walk within like 50 feet of it. Otherwise, like the electricity would arc to you. So the problem with scaling this up is, let's say what I wanted to do was like 5 miles. You couldn't walk within like a half a mile of it without getting electrocuted. So that was the problem with Tesla coils. They did work, but they had sort of practical issues with them. Brian?
I thought you went up and went like this to show that it was harmless, and you went like through it.
He was probably shielded at the time. So like you can, we'll talk more about that later on.
You know what I'm talking about then?
I have no idea what you're talking about.
I saw it on the History Channel, so
Okay.
it's legit.
Hey. Anyway. Okay, this is kind of what we were talking about before. Is that electromagnetic flux? The flux is the electromagnetic field through a loop of wire. So the stronger the field, the more flux, and the closer it is to a magnet, and also the larger the loop area, the more flux is going to be going through it. This is kind of a tricky concept, so I'll try to explain it as best I can here. We'll go through some examples. Okay, and if the flux through a loop of wire changes, that's when a current is produced. So like when we remove the magnet in and out, when the magnet got closer, the flux increased, and the current was produced. And when the magnet got further away, the flux decreased and current was still produced. When it's increasing and decreasing, it produces current in the opposite direction, though. Does that kind of make sense? Okay. So to figure out what direction it's going in, if the flux decreases, you take your right hand. This is our last right hand rule that you got to remember. You take your thumb, point it in the direction of the magnetic field, and your fingers curve in the direction the current goes. So it's kind of like the opposite of what we did before.
Whoa,
So in this one, thumb is magnetic field, fingers are direction the current goes. And if the flux, you use your right hand if the flux decreases, left hand if the flux increases. Okay. Let's go through a couple of examples of these. Okay. So the black lines here are the magnetic field. The red is the loop of wire. So the loop of wire is being pulled out of a magnetic field. So is the flux through the coil going to increase or decrease? Decrease because you're pulling it out of a magnetic field. Does that make sense? Decreasing, you use your right hand. It is decreasing. It's decreasing because it starts off in the magnetic field and it's going to be out of the magnetic field. Do you understand that? So it starts out in, comes out. What you really want to think about is the number of these X's that are going through the loop. So as you pull it out, fewer and fewer of the X's are going to be going through the loop. Does that make sense? Okay, so now we take, it's sort of decreasing, so it's a right hand rule. So our thumb points into the page, and our fingers currently clockwise or counterclockwise? Clockwise. So the current generated in the loop is clockwise. Does that make sense, everybody?
So the arrow to this way,
Arrow, that just means the loop is getting pulled that way,
so
out of the.
that has no effect on it?
That has no effect on it. All that matters is if it's increasing or decreasing.
Alright.
Okay. This time, we're pulling the loop into a magnetic field. So is the flux going to increase or decrease? Increase. So which hand do we use?
Left.
Left. So thumb goes in the direction of the magnetic field. And are your fingers curling clockwise or counterclockwise?
Counter.
Counterclockwise. This one generates a current counterclockwise.
Does it matter if the current is counterclockwise or clockwise? Like, does it make a difference?
It doesn't make a difference practically, but for problems you're going to be doing, I'm going to be asking you about that. Okay. Alright, next one. This time the magnetic field is pointing out of the board. If the loop shrinks, does the flux increase or decrease? How many lines are going through the loop? Are more lines or less lines going through the loop? Less. So the flux decreases. So if the flux decreases, is it a right or left hand rule? Right. So I point our thumb out
Why does it decrease?
because the loop's shrinking. So fewer of these lines are going to be going through the loop, so the flux is decreased. Does that make sense? Okay. So point your right hand rule, point your thumb out, since the little dots mean out of the page, and is your hand curling clockwise or counterclockwise? Counterclockwise. So that's the current loops generated counterclockwise. Alright. Questions about that one? Alright. Next up, a north pole of a magnet is brought toward the loop. Is the flux going to increase or decrease if you're bringing the north pole of a magnet toward the loop? So is the magnetic field going to get stronger or weaker if you bring at the loop if you bring a magnet close to it? Stronger. That means the flux increases. So it's left hand, and for a magnet, does magnetic field go out of the North Pole or into the North Pole? It's like on the first page of your notes. Out of the North Pole. So it's going to be going out of the page, and it is increasing. So which hand?
Left.
Left. So it's going to be going clockwise. How are you guys doing?
Not bad.
Not bad. Okay. One more example of this. Okay. So next up is the current induced in the loop clockwise or counterclockwise again. Alright, so if the current is increasing, is the magnetic field going to be getting stronger or weaker, do you think? Stronger. So the more current going through the wire, the stronger magnetic field it produces. So the flux in this case is increasing. Alright, on top of this wire is a magnetic field going into or out of the page? Out of the page. Right hand rule for that. Everybody understand why it's going out of the page on top of the wire?
Yes.
Okay. So it's increasing and coming out through that loop. So which hand is it? Left. Point your thumb out. Is it curling clockwise or counterclockwise?
Clockwise.
Clockwise. Okay. we'll go through more examples of this. Probably, I feel like some of you guys feel confused.
Well,
I'm not confused, it just takes my
I'm
time.
not confused, I just don't know.
Okay. We'll go through this more if you guys are confused, so don't freak out yet. Okay. Alright. We're not going to go back through these previous 5 slides, but whenever current is induced in a loop of wire, a force opposite direction is moving is generated. Does that kind of make sense? So if you're pulling a loop of wire into or out of a magnetic field, it's harder to pull than it would normally be. Does that make sense to everybody? So like when you're generating electricity, it's harder to like spin the loop of wire, spin the magnet than it would normally be. Okay, so again, this is a generator. Usually how a generator works is you have a loop of wire, you turn it in a magnetic field, and as you're turning it, the flux constantly changes because the area of the loop constantly changes. Does everybody understand that? Okay. Motor is the opposite. You run a current through the loop of wire in the motor, and that generates a force on the loop of wire because it's in a magnetic field. And what you have to have happen is, you see how there's like a little gap right there? The current, because of that little gap and it goes from side to side, the current continuously changes direction to keep the motion going. Right. And last thing, we talked about this a little bit, transformers change the current and the voltage through 2 loops of wire in an alternating current. I think, are we about out of time?
Yeah.
Okay. That's the end. Alright, does anybody have any questions about anything so far? Like I said, we're going to review the right-hand rules a lot more. Hopefully it'll become easier.